You know, it's after lunch, the room's dark, it's hard, I get it. Hello, welcome. Thank you everyone for coming. My name's Dave. I'm going to talk to you today about C#. And I'm going to talk to you about lowering because I like lowering. I like C#. I like to know what the compiler is doing. I find it interesting. I do work for Microsoft, but I don't work on the compiler. I work pretty closely with the compiler team and the Roslyn team. But this is mainly just interest and good practices and things that I think can help you be a better developer. So the first question is, what is lowering? Has anyone heard the term before? Any hands? I can't see any, but there is a really big light there, so maybe. So that's good, because I'm going to explain what it is, so if you'd heard of it, you'd be bored. Let's pretend that we're all in a language design meeting, and we're going to discuss, in our fictional language that looks a lot like C#, how we take a foreach loop and how we compile it to intermediate language, right, IL, which is what .NET code compiles to. And so we're all discussing, you know, strategies, how we're going to do this. What's your favorite IL instruction? What's mine? And in the back corner, there's someone who, I won't say he's lazy, but he likes efficiency, and he likes to do the least work possible. His name is lowering. And he says, you know, why are we discussing this? We don't need a for each statement. We just tell our users, if you want to write a for each, well, you can just write a for loop. And they do the same thing. Right? This code is equivalent. So fine, he's pretty belligerent, so we accept his idea and we start discussing how we're going to compile a for loop to IL instead. And of course, after a few minutes, up pops the hand. Well, we don't really need a for loop, because everyone knows a for loop is just a fancy way of writing a while loop. And this does the same thing. So it's less work for us. Okay, fine. And of course, you can guess what happens a few minutes later, up pops the hand. A while loop is really just a convenient way of using a goto statement. So we don't need any of this, right? And after a few more minutes of talking, actually we get to IL. Now this is the only IL in this talk, because I'm not talking about IL mainly because I have no idea what it does. I mean, it runs my code somehow, but the only thing that well, not the only thing I understand, but I do know what this means. So here we can see a bunch of labels, right? They're line numbers or memory addresses. You can think of them as labels. And this line says blt.s to il24. This is branch if less than, and 224. So if we think about our code, if something is less than something else, and there's stacks involved in this, and we have registers and whatever, we don't worry about that. But if something's less than something else, go to the start. And that's exactly what IL is saying, right? It's pretty clear. The thing is, this is all IL can do. There is no loop construct in IL. There is no block construct. It's just a bunch of instructions and a bunch of branching, which is basically gotos. So everything we write in C# has to eventually get down to this level anyway. So the idea behind lowering is that it's easier to do as much of that work to get to this level in C#, which is a nice language, than it is to do it all in IL. I won't say it's not a nice language, I don't know. So lowering is, we have the compiler take our code and convert it to a lower form, but of the same language. And there's plenty of examples of this in C#. So hopefully we all know what link queries are. And I think link queries is one of the most well-known examples of lowering, even if you didn't know that it was called lowering, because a link query can be written two ways. We can write our query syntax like this, but hopefully most of you know, and I think most people do, that this is equivalent to writing using the method syntax. And in fact, in Roslyn, in Visual Studio, with refactoring, say convert loop to link, there's two options. You convert it to query syntax or method syntax. So these are the same things. The query syntax gets lowered into this form. You might have heard the term syntactic sugar. So lowering is essentially the opposite. Lowering is taking the sugar away. The thing is, I said it's everywhere, right? This code also needs to be lowered because these are extension methods. The way you write an extension method is you use a static method. You mark the first parameter special in, and the compiler lets you kind of pass that first parameter in, but as the thing you're calling it on. But they are also just normal static methods. So this code is actually equivalent to this, right? IEnumerable.select is our static method, and instead of calling it on a collection, we pass our collection in, and our collection is the result of our where. And then we have lambda expressions there. Of course, they need to be lowered as well. And conceptually, they kind of get lowered to this. You can kind of think of them as methods. So what started as a query that looked like upside down SQL can also be written in this really fairly standard C#. And so if you're writing a compiler, you've got to write code that converts this normal C# into IL. It's easier for you to convert the fancy C# into normal C# and then into IL. It's basic code reuse that we all do, right? If you think about the previous example of foreach and for, etc., if you had a method called foreach that compiled a string of code, it'd be much easier to change that code to a for and then call the for method than have 6 methods that all write to IL. Anyway, that's lowering. It's absolutely everywhere. I'm actually just going to switch to Visual Studio for a second. So this is the Roslyn project solution. So Roslyn is the C# compiler, if you weren't aware, and it also includes IDE bits. It used to include a project system, which I work on. Yay. It doesn't anymore. In the compilers folder and under C#, and in the actual compiler here, there's a folder called lowering. And in here, there's not a lot. There's, 10 or so files. This is where all the code lives that does the lowering. And lowering is about rewriting code. So there's a bunch of folders there you can see called rewriter, have rewriter in them. If we look in the local rewriter folder, this is all of the code that lowers C# in place. So these are the simple ones, and I'll talk about a few in a minute. But if we expand this folder, you can see there are heaps of files here. And there's all sorts of weird things you wouldn't think about, like if statement. Let me zoom back out, because hopefully Visual Studio is going to open a file now. Yay. So this is how we lower an if statement. You kind of wouldn't think that if statements need to be lowered, right? That's pretty low-level code. It's an if statement. But if we scroll down, there's a comment here that says what it is. So an if statement has a condition and a block. But remember, in IL, there's no such thing as a block. So the way we write an if is we have to invert it and skip the next bunch of code. So even an if statement gets lowered essentially into a goto. Gotos are everywhere, right? So there's all these files. It's very prevalent. There's a few more examples. So something simple like var message equals NDC Oslo. Var is not a concept that the .NET runtime knows about. It's just the compiler. We know that when we type var, in this case, the compiler will insert a string. Well, that's lowering, right? It has to lower it to code that says string message equals NDC Oslo. The compiler also uses lowering to optimize your code. So if you wrote this code, the compiler sees that these two strings are literals, they can't change, and it sees that you're using the plus operator, and it knows how to do that at compile time. So these two lines of code actually lower to the exact same thing. They both just say string message equals NDC Oslo. If we have our bits of our string coming from somewhere else, then things get a bit different. So if these were constants, the same thing would apply, and all 3 of these lines of codes could be the same. But if they're variables, it still gets lowered. It gets lowered into using the string.concat method, because it's faster than using the plus operator. So there's a tiny bit of optimization that happens during compilation, kind of before compilation, but by lowering. Even something as simple as declaring a decimal is not an intrinsic type in .NET. So this actually, when it gets compiled, would say decimal message, and I guess it probably shouldn't say message, equals new decimal. This is just a normal constructor. There's a convenience way of you to express that, which is the M, but when it gets down to it to compile your code, that convenience was just for you. It's not for the compiler. So why do we care? Why are you all here? Now don't think too hard about this. Nobody leave. It's okay. I'll tell you why I'm here. I like knowing what happens under the covers. I like understanding one layer below where I have to, right? And this applies to life as well. I like to know I like to know how the things I'm using work, and I think it helps you use them better. It helps you utilize them better. My wife had a problem with her OneDrive on her MacBook recently, and of course I work for Microsoft, so it's my fault. And a message popped up. She had no idea what it meant. I don't use a Mac. I haven't for a few years. I didn't really know what it meant either, but it said there was something wrong with Keychain, and I know enough to know that Keychain is where Macs keep their passwords. So I opened Keychain, I found OneDrive, I deleted it, and we tried again. And it worked. I still don't know anything about Macs, I don't know anything about OneDrive for Mac, but by knowing just one little bit lower, I was able to solve a problem. And so I do the same thing with C#. The real concrete reason to know, or one of them, is performance. Take this line of code, fairly simple string concatenation. Count is a number of some kind. This code is perfectly readable to me, but in C#6, I think, we got interpolated strings. And a lot of people find these easier to read, and they have a very good point. When this first came out, where I was working, it seemed like every pull request that was open for any reason, people would also go and fix up all these concatenations that they found and convert them to the new syntax. And that's cool. It's good to clean up code as you go. But every time that happened, I saw a potential performance problem, because interpolated strings like this compile or lower to string.format. So string.format is slower than concatenation. Now, there's a good reason for it to be slower, and in this case, arguably the first line of code is wrong, because the first line of code won't do things like thousands separators, which in Australia would be a comma, but here it's not a comma, right? So except allowing for culture and things in your strings, that's a good thing. This probably should have been string.format, but it is slower. So every time someone changed code, if it had a number in it, great. But if it didn't have a number, probably should have stayed with concatenation. And those kind of details, you only know if you know what the compiler does with your code. Now, the funny thing with this story is that since that time, C#6, excuse me, I think it was about 6 months ago, I actually went looking for this again to suggest a change. And it turns out that a community member, because Roslyn is open source, actually fixed this problem. And now an interpolated string, if it doesn't need culture, it will just lower to string.concat. So there's absolutely no reason not to use them now, which is great, but it's still good to know those, those ins and outs. All right, let's get to the meat of this talk. What does a for each loop do? So we're going to be looking at a lot of code, and it's all going to be on screen. I'm not typing any of this because it's too hard to remember. I'll get it wrong, and then someone will criticize me. So hopefully we're going to have a little bit of an easy entrance into it. It's a bit like a roller coaster, right? We're going to start easy, have a little bit of a tough time, but then it's all right, we'll get back onto an easy path. And then maybe at the end, it maybe goes a little bit too deep. We'll deal with that. There's an expression in Australia, if you're feeling sick from a roller coaster, that you go a bit green around the gills. I don't know if that's an expression in Norway, but just in case. If you start to feel like you're maybe not following along, whatever, yell out, feel free, I'll stop, I'll repeat, whatever. If you really can't handle what's going on, that's okay. You can leave the roller coaster at any time. If you put a green card in, I'll know it's because you're feeling green. So, I'll improve for next time. All right, let's talk about a for each loop. So I've coloured in the body of our loop here green. That's a coincidence, I swear. That's just to say, it's green like a comment is, right? Ignore this. The compiler, it does know what's in your loop, but it can't really know, right? It doesn't know what console.writeLine does, because it would have to go and decompile console.writeLine to find out. So the body of the loop is not important to this discussion, so I've just flagged it there so we can ignore it, and because it kind of moves around a bit. So what does a for each loop look like? Well, you probably know that for each works on IEnumerable. So IEnumerable, which is up here in the top left, has one method called getEnumerator, returns an IEnumerator. IEnumerable, which is in the bottom left, has two methods, one property. It has a current property, which is the current thing we're looking at. Sorry, I'm in the way. It has a moveNext method, which goes and gets the next value, in whatever that may mean for that enumerator, and returns true for whether it succeeded or failed. It's whether it succeeded in getting the next one, it's not whether there's another one to get, which is a minor little quirk, but it's worth knowing. And then there's a reset method, which nobody has ever called, ever in their lives. In fact, the generated enumerators that we'll look at in a minute, they just throw an exception. It's great. And then we have IEnumerable of t, which, obviously when generics came in, we had generic versions of this, so they use a new operator and they strongly type things. Probably in hindsight, if the designers of C# had their way again, they probably would have, generics would have been baked in at the start and this little bit of mess wouldn't exist. But in order to solve this weirdness where there's two IEnumerators or IEnumerables and you can implement both, foreach doesn't actually care about any of these interfaces. Let me demonstrate. So if I type in a foreach loop, let's go var x equals new my enumerator, and I go for var y in x. So let's make an enumerator. So IEnumerable, this is an IEnumerable. Whoops, IEnumerable. IEnumerable has one method called getEnumerator. So get enumerator, easy for you to say. And I can return, I can return null. If the ID stops fire. Oh, I can't because I don't need to return, thank you. Very good. So this myEnumerable is now valid for foreach, kind of, right? There's still a red squiggle here because it's not really. And what you'll see down the bottom, which you can't really see, but anyway, it's complaining because we need more, right? Not only do we need a getEnumerator method, we need that to return a thing that has the other three things. So this is my enumerator. And now we will create a myEnumerator class. And so this needs a current property, which can return 1, a moveNext method, which can return true. I'm going to make it public. Yeah, sure. To 200. Is that better? Cool. And then we needed a public void reset, which does nothing. I've forgotten how to do nothing, so I'm going to do it the old-fashioned way. So this compiles, right? There's no errors in my error list. This now compiles. I've not used any interfaces. I don't even do any enumeration. And in fact, am I still returning null? Yeah, this is just going to throw a null reference exception, right? But the compiler doesn't care. All foreach actually cares about is that you follow this pattern, right? You follow this pattern, doesn't matter about the name. So this is sometimes called duck typing, where if it looks like a duck and it sounds like a duck, we assume it's a duck. I believe the more technically correct, or perhaps just not as funny term, is pattern-based. So foreach is pattern-based. So that's an interesting thing to know. It means you don't need to implement IEnumerable, which can make things easier. So knowing all of these things, how do we actually write a foreach loop? Or how do we lower a foreach loop? So the first thing we do is we create a scope, right? So there's some braces there. They're pretty hard to see by their own. And this is just because our loop variable, our int m in this example, we don't want that to leak out. You can't use that after the foreach is finished, so we have to put in a scope. And then we get our enumerator. And you notice there's no cast to IEnumerable, right? It doesn't matter what values is as long as it satisfies this contract. Now there is an asterisk there, and it is the compiler doesn't allow extension methods called getEnumerator, but that's purely an implementation detail. It's a decision that was made, but that's kind of orthogonal, right? They could easily reverse that decision, change a couple of lines of code, and it would be done. So the compiler kind of doesn't care what values it just, is there a getEnumerator? And if there is, great, I'm going to call it. And so by the same token, the type of E doesn't matter. because we don't care what type it is as long as it satisfies our contract. So I've used var. That's like cheating, right? Like the compiler doesn't really use var because that needs to be lowered. But yeah. Anyway, so then we have a try and a finally. Error handling's good. This is user code that we're surrounding, so we need to be careful. And then we declare our variable, which is int m. And that is exactly what I typed inside my foreach statement. Nothing, no magic happens to that. And then we have a while loop. So a foreach actually gets lowered to a while loop. And then a while loop presumably gets lowered to gotos. And so while we can move next, we do. Inside our while loop, well, we get our current value, and then we call the body of our loop, whatever it is and whatever it does. Pretty simple and straightforward. Does anyone think I've made a mistake on my PowerPoint? You will notice that it's casting to int twice. Why is it casting to int twice? Good question. Thank you for asking. So let's pretend we have a little example off to the side here. We have an object array. We're putting objects into it. These objects happen to be ints. And we're calling a method which takes an object array. And it helps for this example if you imagine there's two different people, right? One person is creating the array and calling the method, and the other person is writing the method, and they don't talk to each other. So we have a method which takes an object array, and then it has a loop in it that says for each int in my array. Now, if you say that in English, it sounds like you're saying go through the array and find the ints. But we can see from the code on the left, that's not what happens. There's no checking here. The lowered code is just blindly casting. So if you were to run this with something other than ints in your object array, it would just throw an invalid cast exception. It would blow up. And possibly you've had this happen to you in code. It's not that uncommon that if something that's not quite of the right type gets in there, you get a cast error. So that's all cool. That kind of makes sense, but it kind of explains one cast, right? I decided that I want ints. I can't dictate what comes out of the current property in this array, so there has to be at least one cast to get from the type in my collection to what I've said I'm going to assume is in my collection. But so what's with the second cast? The second cast is a little harder to explain because it's kind of transparent. But strictly speaking, to put those ints into that object array, we had to cast them to object first. So that's kind of where the second cast comes from. There's one for the type of thing in your collection and one for the type of thing you're iterating. Now, these are probably very often the same thing, but there are reasons and examples where they're not. So let's complicate this example a little bit. And this is very terse because I'm shoving it in the corner. But let's pretend we have three classes. We have a person class, and then we have a customer and an employee. And there could be relationships here, like one could inherit from the other, or they all could inherit from each other, or two could inherit from one. That's kind of unknown, right? But for this example, let's just pretend. So if we construct an array of people and put employees in, that makes sense. Employees are people. And as long as there's a conversion from employee to to person available, that'll work. And then when we're the person writing the method, well, we're getting an array of people and we want to pull out customers. And that makes sense because customers are people too. It's a good slogan. So as long as there's a conversion available from person to customer, our code makes sense. And in fact, person A, who's writing this top 2 lines of code, could supply a custom explicit cast to do this conversion. Person B could supply their custom explicit cast, so one from employee to person and one from person to customer, and all of this code would work. Because the two casts would be employee to person, person to customer. And each of those hops works and makes sense. If we didn't have two casts, though, we'd be going employee to customer, and nobody has provided that relationship, right? These two people haven't talked. So the two casts are for obscure situations like this, but that's the type of stuff you've got to do when you're on the language committee, which is why I'm not. I just read their code and try and explain it afterwards. And then in our finally we have dispose. We call dispose. That's fairly easy. Now, this code is not exactly what the compiler does. There's some liberties here in order to represent it. And the dispose one is a good example. We don't know the type of E in this slide because I have only, certain keywords available to me. The compiler does know the type of E. So when it compiles this code and it does the lowering, it knows if E is disposable, and if it's not, it just doesn't output this line of code. Easier for me to represent it with an if statement. So that's a for each. And if you go and write a for each loop right now and you look in your DLLs and you decompile your IL, you will see not this, because this is a C#4 for each. A C#5 and beyond for each looks a bit different. Watch the while. So, in C#5, they made a breaking change to how for each loops are compiled. And this is it's pretty rare that they make a breaking change like that. And the reason is that in C#4, we got link and we got lambdas, and everyone started using them a lot. Was it 3.5? Anyway, when link came along, everyone started using lambdas a lot. And there was a common problem that lots of people kept running into, where the loops stopped doing what they thought they should do. And to fix this problem, this was the fix. So to understand why, we need to talk about what lambdas do. So lambdas. This is a very simple definition of a lambda. We're defining an action, takes a string parameter, it has a console.writeLine as its body, and then we call our lambda. So this gets lowered, of course. And like I said earlier, you kind of conceptually think it gets lowered like this. So we write out a method, we call our method. But this is actually a problem. And this is a problem, well, a potential problem for memory usage. Because the compiler doesn't know what the body of the lambda does, like it didn't know what the body of the loop does, this could cause the whole class C to have to live on in memory forever. And this can be a big problem. If your class in this case is a Windows form, then it could have a lot of resources that it's holding. Lovely sound. So in order to avoid this, the compiler creates a class, creates a helper class. The helper class gets our method. We assign our action to point to that method, and then we call it. Cool. Except this is a problem. Every time we crawl our lambda, we're now creating a new instance of a class. So in order to prevent memory issues, we're now creating more stuff in RAM. It's kind of silly. So what the compiler actually does is this. This is where we have our first little dip, because this starts to look confusing, right? Just bear with me. So our helper class gets a static read-only instance. So it's a singleton, right? There's only one of them around at a time. And the helper class gets our pointer to our action. So again, static, there's only one of them. When we call our lambda, or when we define our lambda, we check if we've initialized this method of ours, and if we haven't, we point it to the method, and then we call it. So this means we'll now get one helper class, and it doesn't matter how much we call this lambda, there's no more memory head, right? There's an initial overhead, but there's no more. So whenever people say, be careful of lambdas they allocate, this is what they mean. They create instances of these helper classes. And the helper classes, they can be one per lambda. They can be based on the compiler has some smarts to, sometimes combine things together, but there's a lot of little quirks to this. So this is sort of something to watch out for. And the problem with for each loops only occurs when you capture something in a lambda. And when you capture something in a lambda, it goes back to the previous way of doing it anyway, for reasons that hopefully will become clear. So we're going to ignore this for now, just to make life simpler. We're going to ignore this singleton pattern. And we're going to assume that our lambda, defined like this, gets lowered to this. So we have our helper class, pointed to our method, and we call our method. Cool. So the problem comes when we capture variables. So if we define a string, y equals world, and we use it in our lambda, but we're not passing it into our lambda, right? This is we're capturing y. This is where our problems start to manifest that cause them to change from C#4 to 5. So what this looks like on the right-hand side, aside from our body changing, is we get a public property field in our helper class, and instead of the y being a local variable, we're now modifying that field. Every reference to y that would be on this left-hand side actually gets changed to be a reference to y on our helper. So that's not a big deal, right? One new field on a class. But what happens when we change y after we define our lambda? Does this output hello world or hello fish? Anyone? No one's brave enough. It's hello fish. And the reason is that every reference to y gets changed to a point to our field. So we're setting our field y to fish, and then when we call this method, well, it's just using whatever the current value of the field is. So this is a little, quirk of lambdas that people sort of get used to very quickly when they start to use them, when you capture fields. And it's a positive thing, right? It's what you want to happen. You want to capture the variable y, not the value of the variable y. If you wanted the value, you'd pass it in. But so when you introduce this into loops, things get a little bit unexpected. So if we change our loop a little bit to get a lambda in there, we now have a loop through our values like we did before, but instead of just writing out the value, we're going to add a lambda to a collection that will write out the value when it's called. So this is kind of like poor man's task. So m is not passed into our lambda, it's captured. So what happens when we lower this, we create our helper, we assign our loop variable, and then we add our action. So what's going to happen when we run this? We're constantly reassigning the same field. So if this loop went from 1 through 5, instead of outputting 1, 2, 3, 4, 5 when we execute these tasks, it's going to output 5, 5, 5, 5, 5. And this was what people were seeing. They would write link queries against a database, and often what they would do is things like get a list of customers, loop through the list of customers, and then get a list of products. And they would get the products for the last customer associated to every customer. And it was really common, and you could start to see it, you could start to see from the title of the question on Stack Overflow, be like, oh yeah, I know what this is. And fortunately, the workaround was pretty simple, but it affected enough people they decided to change it. So the C#5 change, simply move that inside. So now we get a new helper every time. We're setting a different field. Easy. But you can also see now where that link, or the lambda methods and allocations can start to add up too, because we're getting a new instance created every time we loop through this collection. Any questions on any of that before I continue? Is everyone following? If you've fallen asleep, it's fine, I don't mind. Just put a green in, we'll call it even. Well, before we leave captures, there's one more quirk to be aware of as a perf trap. So I've added to the lambda here a z, because I'm really inventive with my variable names. But this is a field. So what happens when we capture a field? Well, we can't just add a new field called z onto our helper class, because it's not local anymore. So what happens is that we actually add a field to store the reference to the class z comes from. This kind of makes sense if you think about this z here. If you imagine that as this.z, we're really capturing this. Z is, an implementation detail. So as far as memory traps go, we're now back to the situation where if you have a lambda, it can keep the whole class that it's coming from in memory forever. So again, this is easy to work around. So for this problem and for the loop problem, if anyone's still using the C#4 compiler, the solution is you just capture the value yourself in a local, and then you won't have this problem. But this trap still exists, and it actually has to exist because, again, if you think about it, you want your lambda to reference the current value of z whenever it's called. Now, being a class level field, right, this could be changed in another method, could be changed from background thread, could be changed by 3 threads at once. The compiler can't rewrite all of your code. So this is the only way for it to work, it's just a potential trap. So that's the simple case for foreaches. I'm glad that you're all come along with me, that's good. Gets a little bit more interesting now. Because there's also something called iterator methods. And so this is the yield return statement. Hopefully you're familiar with it. This is a very simple use case. We simply go yield return 1, 2, 3, 4, 5. And what happens is, when we run this loop, the first time through this loop, it's going to return a 1, output a 1. And the second time through this loop, it skips the first line of code, and it comes down to the second line of code, conceptually. Obviously, it doesn't actually skip code, right? Because you can't do that, can you? Well, let's work out how it does it. So our for each loop is unchanged, largely. I've written it more simply with the using statement, but it's the same thing. We call get enumerator, we have move next. So already we can see one interesting thing, or one positive thing. Our getInts method is called once. That's good to know, right, when we're thinking about performance. So we call our getEnumerator method on the thing it returns immediately. Our getInts method has been rewritten, and of course we have another helper class. This one's a bit more complicated though, so it's on the next slide. And we're passing -2 in to the constructor. This is kind of important. Remember it for later. So what does our class look like? Well, it implements all of the interfaces, just in case, I guess, IEnumerator of everything. But it does double duty as an IEnumerator and an IEnumerable. Okay, that's interesting. We have 3 fields, a state, a current, and a thread ID. Now, state kind of gives the game away here. It's going to be a state machine. Okay, hopefully we know what state machines are. It's a pretty simple one, so we'll be right. We have to implement our interfaces, so we have current properties that return the current field. And we have a constructor. And the constructor takes in an initial state. Remember, it was -2. It stores the initial state, and it stores the thread that is currently running. So it stores the thread ID for the thread that constructed this, right? The thing that called getInts. Okay? Not getEnumerator, but getInts. And we have a dispose method that doesn't do anything. And I guess there's a reset method that doesn't do anything either because it's part of the interface. So a getEnumerator call looks like this. Starting to get a bit more complicated, I know. It's all right. We'll go through it line by line. So if state is -2, that's our initial state, so it is in our little run through here. And we're still on the same thread, then we set state to 0, everything's fine, and our result is this. We are our own enumerator. Okay? If that's not true, we construct a new helper, but with the initial state of 0. So at the end of this method, we're going to have an enumerator whose state is 0. The thread stuff is because this getInts method, again, it's just sitting there on a class. Anything could be calling it from any thread. You could call it 6 times in a row before you actually iterate over the results. So this enumerator is smart, and it will reuse itself when it can, but if it can't, you get a new one. Again, for performance reasons, these are all interesting things. Yes?
What happens if the
current
managed thread changes in the comparison before the assignments happen?
Good question. What happens if the current thread changes before the assignment happens? That's a very good question. I suspect that, so this is a representation of the code that is written. This is not really the code, right? So I probably should explain this, what I mean this, in more detail. The C# compiler, when it lowers code, it doesn't literally output C# back to itself. Okay? The C# compiler goes through various stages, and most compilers, they parse your code and they parse it into something called a tree, a syntax tree. And when the lowering happens, it's actually at the tree level. So we've worked out what the code means syntactically, and when we output the lowered version, it's actually by just modifying the tree. So it can do some tricky things, like have this comparison be the very first thing that happens or something like that. But in this case, if state was -2 and thread ID changed in here, then potentially this could be a problem. But since it sets state to 0, the next call through to this would fail this check and you get a new enumerator anyway. So I think in practice it would actually be okay. Possibly 2 at exactly the same time might cause a problem. That's something interesting. Maybe look into that later. Anyway, so at the end result of this method, sorry, did I see a hand go up? I can't. Nope, cool. At the end result of this method, we have an enumerator. Our state is 0. We're all happy. We're ready to go. And so this is what our move next method looks like. I mean, obviously this would be under there, right? And so this is our state machine. And other than the fact that it uses funny numbers, that negative numbers for some reason, it's reasonably simple to understand. When our state is 0, our current is 1. We set our state to 1. When our case is 1, our current is 2. We set our state to 2. So this is a state machine that just jumps through our different yield return statements. Now it also sets state to -1. And what that means is I'm busy getting the next value, okay? Because again, the green is user code. The fact that I said yield return 1, it doesn't know that. I could have said yield return, go and call a really slow web service. So this line of code could take ages to run. So the state machine just controls that. And then we get to the end, our current is 5, set state to 5. When state is 5, we set our state to -1 and we just return false, right? There's no more values. So all this is doing is it's kind of like unrolling the loop. And that makes sense because if you look at our original yield return, it's an unrolled loop, right? If you want to return 6 things in order, you can just return 6 things in order, 5 things. So we have these states for our state machine. And we have -2, get enumerator hasn't been called, so we haven't started yet. -1, we're getting the next value. 0, we're ready to go, but no one's started enumerating yet. And then 1 to 4, which is really 1 to n, because it could be any number, where we're just doing nothing. Current is set, we have a value, we're waiting for the next move next call, it may or may not happen. And then 5, or n plus 1, we're finished. There's no more data to get. So that's relatively simple, but that's for a simple series of yield returns. You can, of course, get more complicated. So what happens? How do you unroll a loop if your loop contains a loop? How do you, right? And obviously, again, I've put in 1 and 10. Those could be any numbers. How do you unroll a loop if you don't know how big it is? So there's some changes to our helper when we do this. So the first thing is we get a new field. We're now wrapping someone else's enumerator. We get a dispose method that actually does something. It's got some states again, and we now have a -3. That's new. Welcome to the party. And it calls finally, and finally calls the wrapper's dispose. I don't know why dispose doesn't call dispose, and then finally could call dispose. That feels like more sane to me, but anyway, this is how they did it. So we're wrapping an enumerator. Okay. Our move next method gets a bit more complicated, but that's for the next slide. All we're doing that we can see is we're catching errors and just making sure we clean up and then pass the errors on. Now this is where our roller coaster's going off a cliff. You ready? Things get kind of, there's lots of states here. So let's talk through it from the top. Initially, our state is 0. Right? All of the -2 threading stuff is all the same. When we are ready to run, our state is 0. So we're going to set our state to -1. Now that -1 used to be we're getting the next value. That's not what it means anymore. Now it means we're getting the enumerator that's going to give us our next value. Because remember, we don't know what our value is. We get our enumerator, which again, this is just whatever was typed in. Compiler does nothing to it, doesn't know what it does, other than it has to be an IEnumerable. Then we set our state to -3. Okay, so -3 is now a new intermediate state where we've got something to give us a value, we haven't got the value yet. And don't forget, this is in our moveNext method, so our job is to get the next value. So we come down to here, and well, we're in moveNext, and we wrapped something, so we just pass that moveNext call on. If it can move next, we can move next. We get the current value, our state is 1, we're all good. If it can't move next, we're finished. So call our finally and our dispose, clear the wrapped IEnumerable, and return false, there's no more values. If anything comes in here, so not the initial state, well, if the state isn't 1, then something's gone wrong, right? See, 1 is set here, means we had a value. We never know whether there's another value, right? Move next gets the next value. It doesn't tell you whether there's anything left to get. So we never know that. But if we were successful last time, then we still remain successful, and we try again. So we set state to -3. If we've run out of values, yeah, return false. Does this make sense? Does anyone have any questions? This kind of gets a bit hairy. So we've got a new state now, right? -3 is running, but getting the next value. -1 is also running, but it's getting the other enumerator. -2 is the same, we're doing our thread stuff. 0 is the same, we're waiting. But now we've only got one state. We are suspended, current is ready for you to use, and we're waiting for move next call, but it's also finished because we don't know when it's finished. So that's kind of weird. So let's bring it all together, and let's talk about why it's worth, maybe, in my opinion, knowing about this stuff. This code snippet is completely arbitrary, obviously, and quite convoluted, but it's also relatively short. There's 2 methods, there's 8 sort of real lines of code. And if you were asked about the performance of this method, well, there's nothing that's obviously happening that's very bad, right? We're looping over some stuff. There's an ordering. Okay, so sorting can take time, fine. But everything else, we're just writing to the console. But if you had to think about the performance of this method, knowing what the compiler does to it, it sort of shows you a different picture, right? You can kind of see behind the curtains. So we can see we have a loop. Okay, we know that our loop is going to get rewritten to a while. That's not a big deal. We've got a parameter being passed into getInts. That's okay. We're not closing over everything. Fine. A getInts, well, that's an iterator method. So we know we're going to get a helper class. And we know that if threading is an issue, or if this method is called by lots of things, we could end up with lots of instances of this helper class. So that's interesting. That could be a potential problem. We have a simple yield return. So we're going to have at least one case of our state machine is going to be a simple setting current. Cool, that's fine. But then we have another yield return which is inside a loop. So we're going to wrap an enumerator here. So that's interesting because our enumerator uses min, which is a field, and it uses max, which is a parameter. So our class that we've created to help this now needs a reference to the class that this whole bunch of code is in. So it could hold that reference for a while. And again, there could be hundreds of instances of this class. And we've also got a lambda method in there. So that's going to be another helper class. That lambda method also uses the field. So that's going to have another reference to the same class and the parameter. And so this simple bit of code, you can kind of sort of see it expand in your mind, is actually quite complicated. And if the Wi-Fi is behaving, I can show you exactly how complicated by clicking this link. Sure. Ta-da. Oh. Go Chrome. So this website that is currently loading is called SharpLab. And SharpLab is an awesome website. Yeah, it worked. It's used very frequently by the compiler team. It's not official Microsoft. It's just written by a guy from New Zealand who's a really nice guy. And one of the things it can do is show you what your code looks like. So here on the left is the code from the sample I had. And here on the right is what it looks like when it's decompiled. Now, I've been talking about lowering and what the compiler does before it outputs the C#. This is decompilation, which is slightly different. This is code that has been compiled all the way to IL and then decompiled back again to C#. So there's some minor differences, but not many. And if we scroll down, I mean, the first thing you can sort of see is just how much code there is here, right? There's a lot of stuff going on for our relatively simple example, right? Here's our case state machine. Here we're constructing new instances of classes and things. Here's our actual, I don't know, we're still in the helper class. Oh, there's our reset method. Yes, not supported. Here's our actual code that does the enumeration. So here's our while loop, and here's our getInst method. So all of this code is running for everything, every time you run that code on the left. So when you kind of think about performance, you think about complexity, you can start to see where if you know what the compiler is doing, you have a new perspective on the complexity of some bits of your code. Slides. So if you have enjoyed this trip down into the depths, there's a couple of places you can go to get more things, get more info. So the Roslyn source code is awesome. I'll actually show it in a second with some more examples. Your favorite decompiler is a really good way to do this. Again, not quite exactly the same, but most of them have options to turn off. You have to turn off optimization in the decompiler because it will try to, so if you opened up ILSpy, which is what SharpLab uses internally, and you decompiled that code, it actually would come out looking pretty much the same as what you wrote because it detects all of these patterns the compiler outputs and it reverses them, assuming that's what you want to see. But you can turn them off, and if you turn off all of the optimizations, that's what SharpLab is doing, then you get to see the real code, or at least the equivalent of the IL. And then SharpLab. I really like SharpLab. I've made a couple of contributions to it just to make it a bit nicer to use and things like that. Make it, well, not nicer to use, to make it decompile even more, because I want to see the guts. It's really cool. It can also run code. There's a mouse cursor somewhere, there it is. So you can also run code, you can see the assembler that's outputted, you can see the IL, it's fantastic. And if you click this drop down, you can pick any of the feature branches of Roslyn. So if you want to see what some of the compiler work that's still going on will do, you can switch to a branch, so records, right? Records is something they're thinking about for C#9, it's not in the compiler yet, but if you switch SharpLab to that branch, it will compile your code with that. So you could run code using, you know, a preview essentially, or not even a preview, just a branch build of Roslyn. You can run code and see what it does. The Roslyn source code, though, I was going to show off a couple of things. The cool thing about the Roslyn source code is the comments. Let me find the foreach statement. So this is foreach. This is the method that rewrites foreaches. This is what we've been talking about. And there's a couple of things. So firstly, there's 4 different rewriters for foreach. Yes. Oh, this one. Thank you. I must have done that on the other instance of Visual Studio. So there's 4 different ways that it will compile a foreach. So a single dimensional array here has a specific overload to optimize that case. A multi-dimensional array has a specific overload to optimize that case. So there's all sorts of optimizations in here. The cool thing is these comments. These comments tell you what they're going to do, tell you what the equivalent C# they'll be outputting is, right? And so this is the one we've just been talking about. Here's our 2 casts. This stuff is for async enumerable, which is new, but it's essentially the same concept. There's just async methods. So this is the stuff you want to start by looking at the comments, because that's written in C#. If we scroll down to look at the actual code, right, here is the line of code that lowers to our getEnumerator call. And you kind of have to really get used to this before you can read it. I mean, I can't really read it. It's not, you know, it's not C#. This is 2 casts and reading of 1 property, right? This is complicated stuff because this is modifying the tree, the syntax tree. You can kind of see, so this is a make conversion, so that's a cast. Then there's another make conversion, that's another cast, right? We have our, where are we? We have the element type, right? So one cast is to the element type in the collection. The other type is to the iteration variable type, right? The one that you typed in. So you can slowly get used to this as you explore if you want to, but the comments is really where it's at. And it's all broken down really nicely. If we scroll down, we should see, that's not it. Somewhere in here, here we go. So this is a special overload for collections that you're for-eaching through if they have an indexer, because it can make things slightly faster and it doesn't go through IEnumerable at all. The compiler still requires you to implement IEnumerable or it won't compile, but when it gets down to the lowering phase, it's like, well, you know what? I won't bother with that. If it can work out you've got an indexer, this will be faster. So there's all sorts of these optimizations and things if you want to explore. But that's it from me. So if there's any questions, you may shout out. Otherwise, I'll be hanging around. Otherwise, you can go beat everyone else to the food by 5 minutes. Thank you.